All right, good afternoon, everyone. Hope you had a good weekend. So today is one of the most important days of the semester in terms of what we'll learn and how important it is for answering a lot of questions. Often we will, when trying to understand whether something is good or bad, we'll appeal to something called the bias variance trade-off, which is what we're going to learn today. So last time, we started by establishing our statistical model, which we're going to use for analysis. So in this model, the true targets are going to be generated from some noiseless function, f of x. X is the features, plus some independent noise that is zero mean and has a variance of sigma squared. And so this model is going to be responsible for generating our data for test and training. When we deal with test quantities, we won't use a subscript. When we deal with training quantities, we'll see the subscript I. And then we have a prediction model. The prediction model has a possibly different function, f hat, which operates on the features, but also involves some parameters beta. And we're going to assume that the betas that we put in there are trained from some from the training set. So this is from our training data. So we're going to train them. So, in a lot of cases, we're going to train them using least squares. But this is our prediction model, and the predicted targets are y hat. And the thing we want to analyze today is the mean squared error on the predicted targets for a given x. So that has this expression. So here we see we're looking at the difference between the true and predicted targets squared, and we're doing a conditional expectation. So this is a statistical average, but we are holding the test features constant for doing this average. Okay, so essentially what we're removing with this averaging is we're removing all the noise in the test targets. So these guys are noisy. And then these y hats are variable because they were designed with some training data. And the training data we're also treating as random. Okay, so that's our objective, is to do this analysis. And last time I wrote that this is the statistical version of the normalized RSS. And that's actually not exactly true. If you remove the conditioning on x, then it is. So we're going to talk about that later today. So I'll write here, if conditioning on x is removed. Because when we condition on x, we are just looking at the error we expect for that particular test feature x. Whereas when we define this normalized test RSS, or any kind of test RSS, we're actually trying to do an average over our test set. And hopefully our test set is big enough to tell us what happens on average, not just what happens for a very specific feature vector x. Okay, all right. Any questions about the statistical model? Okay, so let's go to this page. So it looks like a big, ugly derivation, but I hope to convince you that it's not too bad. And essentially, we're going to be applying some of these properties here. So one of the properties of expectation that we saw was linearity. Another important property we saw was that you can split an expectation of a product into a product of expectations when those random variables are independent. Then when we dealt with conditional expectation, we saw that essentially what it means when you when you condition on one, or whether you say A is given, that means for the purposes of doing this expectation, you're going to treat A as deterministic. So if this was deterministic, then we could pull it out of the expectation, and that's what's happening here. We also saw that if two random variables are statistically independent, then when you condition on one, it has no effect on the other with regards to this expectation. So the conditioning can be removed, and you just have the original expectation like that. And we saw one other thing. I'm not sure we're going to use this today, but the law of total expectation. And just to emphasize that this one does not require any sort of independence. The only one here that requires independence is this middle one. Okay. All right, so let's start to analyze the mean squared error. So here we begin. This is the definition from the previous page. So the first thing we do is we plug in the definition of y from our model. This is the noiseless f plus the noise epsilon. That's what y is. And then for y hat, that was this f hat. So just plugging in the definitions. Okay, the next step is to think of this as a squared difference between this term and this term. Actually, no, sorry, I did that wrong. Between this term and a squared sum of that term and that term. And so that will allow us to expand this quadratic. So we're going to have the first term squared. Then we're going to have the cross products between the first term and the second term. That's this. And then we're going to have the last term squared here. Okay, so everything hopefully is very straightforward so far. Okay, now the next thing we're going to do is we're going to apply the linearity property. We have an expectation of a sum of 3 terms. We know that that can be written as the sum of the expectations. So we have the expectation of the first, and mind you, these are all conditional expectations where we're conditioning on x. So we have this expectation of epsilon squared. Let's look at the last one. That's just going to be this one. And then we're going to have the expectation of this cross product. So we're going to simplify that a little bit. So think of expectation of this here, and this is actually expectation of this given x. So let's first think, what is random inside that expectation? Or what do we need to treat as random? So remember that the x, because we're conditioning on it, that is being held, it's been treated as if it was deterministic. So don't think of the x as random. We have a couple other random things, though. We have this noise, and we have these parameters which were learned from the training data. So are these guys independent? No. Yes. They are independent because this is a test quantity, this is a training quantity, and what happens at test and training are statistically independent. Okay, so those guys are independent. And so what does that mean then about this expectation or a conditional expectation? What can we do? We have the product. We want to simplify it. So rather than looking at the expectation of the product, we can actually split it into a product of expectations. Expectation of the first part, expectation of the second part. Okay, so here's the expectation of the first part. Here's the expectation of the second part. Okay, any questions on what we did there? Okay. Now we can go a little further. Let's look at the first part. So here we have the expected test noise given the test features. So let's think about those quantities. So is the test noise dependent on the test features? No, they're statistically independent. That means that we can use this. That means that conditioning on those test features has no effect on this expectation. We can basically ignore it for the purpose of the expectation. So that means that this is really just expected value of epsilon. Right? And what do we know about the expected value of epsilon? Anybody remember? What did we say at the beginning? 0 mean, right? So it's that equals 0. So as a result, because this first term equals 0, then we don't even have to worry about the second term. This whole thing goes to 0. And then we only have to think about the first and the last terms. Okay. Any questions with what we did there? Okay, great. So now, let's also work on this term. So we have the same thing going on. Epsilon is independent of x. Therefore, for the purposes of this expectation, we can basically just forget about the x. So we get this is equal to the expected value of epsilon squared. And what do we remember about expected value of a random variable squared? How can we write that in terms of things we more commonly deal with? Variance plus
expectation
plus the squared mean, exactly. So the variance of epsilon squared on the previous page was defined as sigma squared, and the squared mean is what? 0, because the mean is 0. So 0 squared. Okay, so as a result, this first term here just reduces to sigma squared. And that was pretty easy. The thing that's going to require a bit more work is this last term here. Any questions so far? Okay, so let's try to attack this last term. So what I'm going to do is something that might be a little non-intuitive if you haven't seen this kind of stuff before. But what I'm going to do is I'm going to subtract and add an identical quantity in the middle, which is basically like putting in a 0. And then that's sort of a clever little trick. And then I'm going to look at the first part. Think of that as one unit, and this is another unit. And then what I have is the first plus the second quantity squared. Okay, so we can expand this into the first part squared. And then using linearity, we can put the conditional expectation on that alone. Plus, then we have the last term squared. So that's this part. And then we have the cross product, first times the second. And that one we're going to have to talk about more. Turns out in this step, we're really not going to do any simplification to these. We're just going to leave them as is. We really need to work on the cross term, which is the expected product of that and that. Don't think about the square now. So we are taking an expectation conditional on x. Remember, that means that we think of x as deterministic. So when you look at the first term, is there any randomness here in this term? How many people think there's some randomness there? Okay, so if this expectation was not there, yes, this would be random. But we're basically taking the expectation of this quantity given x. So that means when I take the expectation, it basically removes all the randomness except for x. So x, we could still think of this as a random quantity. This expectation would be a function of that random x, but there's no more randomness due to the beta hat because I remove that randomness by averaging out any variation that did not result from x. Does that make sense? So because there's this expectation here, and because we're conditioning on x, basically this whole thing is deterministic. You can think about it as deterministic for the purposes of this larger expectation we're working on. Okay. So is that clear? These are the sort of things, when you're seeing it for the first time, it might not be so obvious, but the more of these you see, easier it gets. Okay, so again, we're looking for the expectation of this thing times this thing. And we just determined that the first one is essentially deterministic for the purposes of this expectation because we're conditioning on x. So that means you can pull this out of the expectation, or in other words, slide the expectation in and just look at this times the expected value of this part. So that's what we have down here. We've pulled out the first part, and now we're looking at the expected value of the second part here. Of course, this is again another conditional expectation. So, does anybody see what's going to happen here? Or I guess it's kind of clear it's going to go to 0. Does anybody have an explanation of why this goes to 0? Anybody brave enough? Yeah.
Because the expectation value of the expectation value just gives the regular expectation value, and that cancels with the second term, which just has one expectation value.
Yes, exactly. So again, this is just like this other thing we analyze here. So this guy, if it's random at all, it's only random due to the x. However, when we do this expectation, we're conditioning on that x. So we're treating that x as if it was deterministic, at which point this whole thing looks deterministic from the point of view of this expectation. On the other hand, this thing is random because of the fluctuations in this. And so I just get, but by linearity, I can look at the expected value of the first minus the expected value of the second. And so when I apply this expected value to this term, I get exactly the same thing as this. And so when I subtract them, they cancel, and we get 0. Okay. Which is nice because this whole thing then goes away. We don't have to worry about it. All right, any questions on that last part? Okay, so that essentially leaves us with the equation we're looking for, which is this bias variance decomposition of the mean squared error. So let's take a step back and look at this. We essentially have 3 terms now. The first term is called the irreducible error because essentially there's no way to get rid of this term. So let's look at where this comes from. If we go back to our model here, imagine that we are doing the very best thing we possibly can, which would be to set our predicted model exactly to fx. That's the best we can possibly do, right? So in that case, the difference between y hat and y will be exactly epsilon. But epsilon is something that's unpredictable because it's some test quantity that we never have access to at the time of training. So there's no way to predict it. So this difference here at that point is just epsilon squared. And we said that the variance, or the average value of epsilon squared, is just sigma squared. So this is sort of the best you could possibly do is to get sigma squared. In other words, set all this other stuff to 0. That's what happens when you have a perfect estimator. Okay, in practice, we don't have a perfect estimator, so we also have some positive terms here. But these 2 terms have very different meanings or interpretations. So the first one, when we look at it, is the difference between the true model and the average value of the predicted model for a given test feature x. Okay, so in order to make, and then notice there's a squaring of this whole thing. We call this thing inside the square the bias. A way to write it that's a little bit more general is it's the average, or the expected value of the difference between the target and the prediction for a given feature vector x. Okay, so it's possible in many cases to make the bias 0, which essentially means that on average, your predictions are perfect. But that doesn't mean that they're ever perfect on a case-by-case basis. It just means on average, over all the randomness here, which, okay, what's random? Over all training data sets, essentially that's what is, actually over all training data sets and over all test noises, if you average over all that stuff, if you have an agreement between the true noiseless model here and this average prediction model, you can set the bias to 0. And we'll see this occur in the experiments. So this is one thing that can happen. But of course, if this is non-zero, then the squared bias will contribute to your mean squared error. Okay, so again, this is about being good on average. It's possible to be good on average. That's not too difficult. This next part is about how the predictor deviates from its average. So notice there's no true model here anywhere. This is all about the predictor, how far it deviates from its average value. And we're looking at the expected squared value, so you can actually say this is like the variance on the prediction y hat for a given x. Okay, so even if you have an estimator, a predictor, which gets your bias to 0, that does not mean it's going to have small mean squared error because it could have a lot of fluctuations around its average value. So on average, it's great, but it has huge variations around the average. It could be terrible. Okay, so those are the three terms: irreducible error, bias squared, and variance. And as we'll talk about, a lot of design questions can be answered in terms of this. You often want to do something like minimize your mean squared error, and you often see a trade-off between making the bias small and making the variance small. You can do one or the other, but you can't do both. So we'll see more of that coming up. Are there any questions about anything here? Yes.
In the bias term, when you have written f of x minus expected value of f hat is expected value of y minus y hat,
Mm-hmm.
where is the noise term the epsilon? Because y is
Yeah.
technically equal to f of x plus epsilon, right?
Right. Okay, let's look at it. So inside here, we have f of x plus epsilon minus f of x and beta. Right? So this is just from the definition of y is this, the definition of y hat is this. So what happens is, because I'm conditioning on x, I can pull this out, which gives me this. Now, the next thing is the expected value of epsilon in our model is 0. So that's gone, and then the only thing left is the expected value of this. So that's what happens. Okay, good. Any other questions? Okay, so this might seem like a lot of math. Oh, yeah. So, and then this mean squared error is all about what happens for a very specific feature vector x. You may not really care about what happens for a specific feature vector. You just want to know how good your model is going to be on average when you use it after you design it. And then you need to average over all the possible x's that you will expect to see. Okay, so that would be just the mean squared error without any x's. So here we're going to take the expected value of our x conditional mean squared error over x. So that will remove all the randomness due to those possibly different x's, in which case, of course, this first term doesn't change. The second term, now you just have the expected squared bias. In the third term, you have the expected variance. Okay, and so all these expectations are doing, they're taking out the randomness due to all the possible test feature vectors that you can see. Okay, and this guy is the one that is similar to the normalized RSS test. The normalized RSS test is just the sample estimator of this mean squared error. So this is like the theoretical quantity, and then in any given experiment, we can compute that normalized RSS, and that will be our estimate of this. If we take a lot of averages, it should converge to this. And we'll talk about that a little bit later today. Okay, good. Any questions on anything on this page? Okay, so there's a very cool demo that I think really helps to put everything together and understand what's going on here. So let me first describe what is actually happening in the demo. And let's go all the way back to, I think it was when we first started talking about the demo. Okay, yeah, these pictures. Okay, so if you remember in our demo, we generate a number of noisy true samples. So these are like our y's, except these are the training y's, the yi's. Based on those, we do some, and here in red, remember, this is the true noiseless model. So that's basically, it's like you generate points along the red curve, but then you add noise to them, and that's what gives you the deviations around the red curve. Then, from those training samples, we do our least squares polynomial fit. And as you can see, it's not perfect, but the green curve is pretty good. right? But it's definitely not perfect. So now, this is what happens with one training set. Imagine you do this with another training set. What you'll find is the green curve will look a little different. It will be pretty close to the red curve, but it will be a little bit different. Every time you do this, you'll get a slightly different green curve because every time you do it, you're using different training data. And so that's this variability. That's the random beta hats are the variability due to the variability in the training data. Okay, so now when you look at the green curve, none of your predictions are perfect. There are isolated points where the green and red curves cross, in which case for that exact X, you get the perfect prediction, but you move away from that, it's imperfect. Okay, so now let's go back. Oh, and we also did the same experiment with linear models where we got a green line. And we also did it with d equals 15, and we got this green curve. I think I might have updated the picture a little bit since last time. I think last time it was doing this, but it sort of depends on the data, what exactly is going to happen. Okay, so now let's get back to where we were. So what I did for the curves I'm about to show you is I ran this experiment 100 times. 100 times I generated training data, fit some beta hats, and created a prediction, in this case a prediction line, a little bit different for every 100 experiments. Okay, and so you have just a bunch of different green lines that are just slightly different. And what I'm showing you here by this solid green line is their average. And then with these error bars, I'm showing you the standard deviation. Okay, not the standard error, just the standard deviation. So you can see that there's some variability in the intercept. The whole line is moving up and down a bit. But there's also variability in the slope in that the error bars on the edges are bigger than the error bars in the middle. So it's wiggling around, steeper, less steep, also up and down. But these error bars show you exactly how much it's wiggling around. Okay. So, and again, the red is the true model. So now the bias, which we just discussed, the bias is the gap between the red and green curves, right? Because the red curve is the average value of y given x. Okay, because this is x on this axis. So you can see the average value of y given x changes depending on what x you're at. And then this green curve here, the middle part, this is the expected value of y hat given x for the case of a linear model, d equals 1. Okay, so the bias, remember the bias is the difference between these quantities, and so that's going to be the gap. So there are a few isolated points like the origin, 0, where there's no bias. And here's another sort of weird x where there's happens to be no bias right there. But for all the other values of x, you can see there's quite a big gap here between the model, the average prediction, and the true noiseless prediction. So you would say that this is biased. It has considerably high bias. Okay, so that's the situation at d equals 1. Any questions about that? So now let's look at what happens at d equals 3. So when you look at d equals 3, you don't even see the red line. The green line is completely hiding the red line. It's exactly on top. This is unbiased. There's no bias at all. And again, the green curve is what's happening on average. So every time I ran these 100 experiments, though, what I had was a slightly different polynomial curve. Sometimes it was a little higher, a little lower, different shape. And so there was a lot of variability. So I never, ever got the correct prediction on any given experimental run. For any given training set, it's never perfect. But on average, across many training sets, it's perfect. Does that make sense? So that's an important distinction. Also, the So this is unbiased. And when you look at the error bars, you can see that they're a little bit larger. They're a little bit larger than these. These are a little bit larger than these, maybe. But it's not really too bad. So we might say that the first case had low variance. Remember, variance is the deviation of the green prediction from its average. So that's what's being shown by those error bars. Here, medium variance. No bias, medium variance. Okay, so what happens now as we go to d equals 14? So maybe surprisingly, what happens on average is actually fine. The green curve is still almost perfectly, or in theory, it would be perfect. It's almost perfectly covering the red curve. The reason why the plot is not perfect because I only used 100 averages. If you would use an infinite number of averages, then you would find that the green curve would lie perfectly on top of the red. But the big thing that you can see is different is it has huge variance, especially when you get out to the edges. So this model, as we know, we saw earlier, this is not a good model. But the problems with the model are not what happens on average. On average, it's fine. It's what happens every realization of this model is going to be far from its average. And that is where the error is coming from. No bias, high variance. Okay, so yeah, green error bars are basically the square root of the conditional variance or the conditional standard deviation. Okay, and these plots are just visual aid to understand the difference between bias and variance, or sort of what's happening here. So this would be just like a target. You're shooting arrows or darts at a target. And this would be a case of a situation where there is relatively low variance. You have, all the darts are close together, but they're all quite far from the target. So they're consistent, but it's off. In the middle case, this is the best. You have relatively small variance, and they're exactly centered at the target. And then on the right here, you have the case where, yes, they're centered on the target, but they have a high variance. So these are not ideal from the mean squared error perspective. This might be the best option. Okay, so hopefully this is kind of helping to understand or explain what this is, how this is working. You're decomposing into irreducible error, squared bias, and variance. And it's a really useful way to think of any estimator into those three components. Are there any questions on this picture here? I think if you understand the picture, you understand maybe most of the main ideas. There have to be some questions. Yeah.
How would it be different if instead of taking you have 100 data sets, you did a regression on each one and average it? Instead you combine all 100 data sets into one big data set and you do a regression. How would that be a lot different?
Yeah, it would be different. But there's also a few different things about it too. We'll talk about that very soon, but just from a high level perspective, the reason we're doing the average here is not because this is not giving us a design. This is actually giving us 100 different designs, right? The technique you mentioned is actually giving you one design. This is giving you 100 different designs, and we're only computing the 100 so that we can evaluate the mean and the variance. That's the only reason we're doing this, is just to try to analyze things. Right? We're not doing this as a design strategy. Like, given all that data, we would never design 100 different predictors, because what are we going to do with these 100 predictors? Like, what you suggest is a lot more reasonable. You have all that data, just use it to get one predictor. So we're just doing this as a way with an experiment of approximating these statistical quantities. So we have no way, I don't think there's any closed analytical way to derive this for our polynomial model, perfectly at least. So we're just doing this as a numerical approximation to the things we would like to analyze. Okay, any other questions? Yes.
Is the bias and variance related to some extent, like, if I use a large number or a small number?
Well, the bias and variance are almost separate. Like we've tried to take this mean squared error and split it into things that are almost unrelated, conceptually different, so that we can understand the overall thing easier by splitting it into its components. So I would say, yeah, they're not really related. They're kind of opposites. You know, one of them is about how far you are from the target on average, and the second one is like how much do you deviate from your average. So those are pretty different. Okay. Any other questions? Okay. Yes.
Follow-up question, would you not just take like the average of the beta coefficients and use that as a model? Like in this case for D equals 3?
So because our prediction is linear in beta, if you have a whole bunch of betas, you can average the models and that will average the y-hats as well. Just because,
Does that give us the model that we wanted?
yeah, if you had all those, you could simply average the prediction coefficients and you would get this, you know, much better model. That's what you could do in this case.
Would that be better than the model of all the data combined?
It would be identical. Yeah. In this case, it would be the same. A lot of the more sophisticated models are not linear in the betas, and so you can't do that. I mean, you can do it, and it's actually it's something that we will talk about in Unit 12, I think, or maybe it's, sorry, Unit 11, I think. But that's called ensembling, where you have a bunch of models. Maybe the models are very different. Like maybe one is a linear model, maybe one is a neural network, maybe one is something else. And you think they're all good, but in different ways. And you want to combine them to get the best of, you know, of everything. You can try to average them, or there's other things you can do to try to combine them. And that actually is, in general, a good thing to do. It's something people study and they do. For this linear case, if you did that, you would get exactly the same as using all the data once. But again, that's not why we're doing 100 experiments. We're doing 100 experiments just to make these plots to demonstrate what we mean by variance versus bias and so on. Okay, all right, great questions. So now I think to answer actually the question that you just raised here, you know, what do you get when you have more data? How does that help you? So we're going to look at the specific case of least squares linear regression. So that's a model. Okay, so what we're going to do is we're going to assume that the true noiseless function is linear, like we saw in Unit 2, with some model order D true. And this noise, now we're going to assume that it's Gaussian to make the analysis a little bit easier. Zero mean sigma squared. We're also going to assume that our model has this same linear form, except that maybe we have a different model order D than the truth. Maybe we underestimate it or overestimate it, or maybe we get it perfectly. But the forms of the models are the same. Okay, so these are the things we have. And in fact, this covers polynomial regression, right? Because we saw that polynomial regression is just like a particular way of constructing your feature data. You start with like a lone x, and then you take it to different polynomial orders, and from there you can build these. So this also applies to the experiment we just did. It's just going to be a little bit more of a theoretical analysis where we can go a little deeper because now we're being more specific about this simple model. So there's basically 4 results here. And the results look at the relationship between the number of training samples, n, and the model order that you assume, which is D. Okay, so the first case, if you have fewer training samples than the total number of coefficients, the total number of betas, which is, here you have D of them, here you have 1, Okay, if you have this situation, that's not an ideal situation because as we saw before, there's this A transpose A matrix that in this case is not invertible. So what that means is that you can't directly compute the least squares solution. In fact, there's an infinite number of beta vectors that will give you the same exact performance. So we don't even really know how to define the least squares solution. It can be one of many. So in this case, we're not really going to study things further because it's not so interesting. Put this in yellow. So if this happens, the least squares solution is undefined. So we'll just hope that doesn't happen. And in most machine learning experiments, you have way more training data than you do features like this. Okay, so let's move on. So the rest of the cases now will focus on the fact of having enough training data to avoid this problem here. So the first case we'll look at is what happens when the assumed model order is less than the true one. So it's not difficult to prove that y hat will be biased. And we call this underfitting. It's simply too simple. So we saw an example of this here. D was 1, D true was 3, and we had bias. Okay. Now, if we look at the case where we have enough training data, and now our model order is equal or greater to the true one, then we find that the predictions are unbiased. In other words, this happens. Unbiased means the bias is 0. And that's exactly what we saw in these two pictures on the right here. So on average, the model prediction was the same as the average target. Okay, so maybe that's not too surprising given the results that we saw. Any questions on that so far? Okay, so the probably more interesting one is that you can actually analyze, in this case, the variance itself. So to do this analysis, it's a bit more involved, and we have to assume that the number of samples is really large so that a particular sample average that arises can approximate the true expectation. The details are in this handout. But let's just assume we have lots of training data. And once again, we're going to assume that we have a model order, assumed model order that's at least as large as the truth. So now we know that the bias is 0, but what's interesting is that the variance, we can derive this analytically. So the variance is going to be the model order plus 1 divided by the number of samples times that noise variance. Okay, so this tells us a lot. So one way to think about it is, let's imagine that your training size is fixed. Someone just gives you a data set, and now you're thinking to yourself, how complex should I make my model? Well, here you can see that as you increase the complexity D, you get a linear increase in the expected variance. It just goes up linearly. And so this is maybe not too surprising given what we saw here. Okay, so that tells you that there's a penalty if you make your model too complex for a fixed training data set size. And this is why we don't want to use overly complex models. So a few times throughout the semester, I've asked you to raise your hands. What do you think? Should we use as many coefficients as we have? And the correct answer has been, unless you focus only on the training RSS. For test quantities, the answer is no. You have to be careful. If you make your model too complex, it hurts you, and now we know why. It hurts you not in terms of bias, it hurts you in terms of variance. That's how it hurts you. We also see now if you choose your model too simple, well, your variance could be low, but your bias could be large. So that's the danger of a too simple model. There's another way we can understand this, which is if you have a model of fixed complexity D and you have access to more and more data, how does that help you? Well, now you can see that as n gets large, your variance gets smaller. So this is why we like large data sets, large training sets, is that they reduce our variance. So a lot of insights from this analysis. Okay, so any questions on this? Yes.
So what does it mean by X has same distribution as Xi? Does it mean that all of the samples have the same distribution?
Yeah, but we can remove that because actually, we already assumed that here. Yeah, so we're assuming that the tests and training are coming from the same distribution. So yeah, if that's distracting, you can forget about it. Okay, any other? Yes.
So it looks like you have a very interesting case where n is just, I suppose that's actually what you have on there, but if n is just one greater than d, but
Oh, yeah. Yeah, if n is just greater than 1, if n equals d plus 1, then it turns out that the variance coincides with the additive noise variance. Yeah, just how it turns out. I guess that's another thing also we didn't talk about is the role of sigma squared here. You can see that the amount of noise in those targets just makes everything worse. So if you have a data set that's really clean, then your variance is just a lot smaller than a data set that has a lot of noise in it, a lot of unpredictability. As that unpredictability increases, the variance is the part that suffers. The bias doesn't care about that. It's the variance that suffers.
But the assumption is that n is much greater than d.
This assumption is mainly for the analysis to go through. So when n is not gigantic, then the situation is just hard to analyze precisely. You have to make a lot of, or you have to know a lot more about the specific distributions and how they behave. But when you have a lot of training data, then you can derive something that holds in general, and that's where we get this. So you can just think about this as like, when you have a lot of training data, you don't have to worry about weird things that can happen when you, special cases if you just have a small training set.
I mean, and n cannot be d plus 1, right? Because
Yeah, that's right, yes. In this case, this holds, at least this holds precisely when n is much greater than d. Yeah, that's a good point. Question?
Does this hold even if the noise is in the Gaussian distribution?
I have to look at the derivation. Yeah, I can't remember. If I wrote it here, I think at least I might have used that at one point in the derivation, just for one step. But I don't know. The derivation had different iterations, and like I don't need this, so yeah, I need to look over. But Gaussian distribution is one of the simplest and easiest to work with, so it's often what gives you the cleanest results. Okay, yeah, so even if this is not holding exactly, the trend still holds in general. And this is sort of the point of the next slide. Even though we focused on polynomials and linear regression, similar trends hold for general models. The important point is that there's usually a trade-off between bias and variance. And the picture that we want to look at looks like this. So here we have the error, which let's say is mean squared error. And here we have model complexity, going from simple to complex as you go right. So here's our mean squared error. You can see that there's a sweet spot for model complexity in the middle. When you look at the bias term, when you have a very simple model, the bias starts out high. As your model gets more and more complicated, then your bias decreases. On the other hand, the variance, when you have a simple model, is low, but as your model gets complicated, the variance increases. And details of these curves depend exactly how you construct your predictor and exactly how your data set behaves. But at the end of the day, things tend to have this form. There's a sort of sweet spot in terms of trading off between the effects of bias and the effects of variance that's somewhere in the middle. You don't want to make your model too simple or too complex. And you can always understand it from this perspective. Okay. Keep in mind that the curves also depend on the number of training samples. So, because we said that that has an effect. So, if you have a certain number of training samples, maybe it looks like this. If you add more training samples, then maybe your variance doesn't grow as quickly, which means your optimal complexity has moved over here. Okay, so this is a moving target depending on how many training samples you have. Okay, great. Any questions on this? Okay, so we'll keep coming back to this bias variance trade-off throughout the semester. And let me just get into only a couple slides left. Okay, so one thing that I've talked about a few times anecdotally was biased versus unbiased sample estimators. So let's tackle this now that we have all the tools. So essentially, okay, so to set things up, imagine that we have some random variable z. It comes from some distribution. It could be Gaussian, it could be uniform, it could be anything, as long as it has a finite mean and variance. And let's say that the mean, the true mean, happens to be mu, and the true variance happens to be v. Now, I would love to know mu and v, but I don't, let's say, know this random variable. I don't know what describes it. All I have are n independent realizations of that random variable. And so my task is to estimate the mean and variance from those realizations. So the usual way we do this, we saw this back in Unit 1, is for the mean. So let's say estimating mu. The usual way we do it is we take the sample mean. So we just take the sample average of our n different z quantities, and let's call the result z bar like we did before. So the question now is, how does z bar relate to the true mean mu? So is it going to be the same? What do you think? How many people think, let's say I have a Gaussian z. How many people think mu will be the same as z bar? Okay. Hopefully no one. If you think about it, Gaussians are generating just floating point type numbers, right? Like just very random on the real line numbers. If you average any finite number of them, you're going to get, let's say you have a zero mean Gaussian. So you know mu is 0. If you average zero mean Gaussians, you will never get 0 unless n goes all the way to infinity. You're just going to get some number, maybe it's close to 0, maybe it's very close to 0, but it's never going to be exactly 0. Okay, so that's the point, is that you're never going to get a perfect agreement between mu and z bar. However, if you think statistically, like, let's think of z bar itself as random. Because if I think of each of these realizations as random draws, when I do one experiment, I'm going to get one z bar. If I repeat my experiment, I'm going to get a different z bar. And so now I can think of z bar as a random variable, which is just an average of other random variables. So from that perspective, we can look at the average value of z bar, and this one is exactly mu. So this one is perfect. This is what we call unbiased. So z bar is an unbiased estimate of mu. That's a really nice thing. You know that on average your z bars are correct, even though on any specific experiment they're not correct. But on average they're correct, so feel good in using them. Okay. So any questions about that? Okay, so now you might say, all right, I know they're correct on average, but I know they're never correct individually. So how good are they? So one thing you can look at is you can look at the variance, which is the average deviation between z bar and the truth, right? Average squared deviation. So this is the variance on z bar. And it's not too difficult to prove this, but in this handout, you can prove that that variance is V over N. Okay, so this is variance of Z is V over N. So here what we see is that as the number of samples you have N grows, you get a better and better estimate of, or your Z bar gets better and better. It gets closer and closer to its mean, which is perfect. And this, in fact, is just the squared version of the standard error. So I said I would explain standard error to you. This is the explanation. So this holds anytime you have any random variable. It could be RSS, it could be whatever you want. And you have, n realizations of it, and you want to you want to estimate the mean. So you do this average. And now you ask, how good is my average? Well, this is how good it is from the variance perspective. If you want to take the square root to make it the units the same as the original z's, you can take the square root, and that gives you the standard error. So this is where standard error comes from. It's just the variance, or standard error squared is the variance over the number of terms you used in the average. Okay. So, any questions on those? Yes.
So is standard error a sample estimator then of the standard deviation of Z?
So okay, so the one that we learned, you could say, is like the sample estimator of this, right? Because we used, we don't know the exact V, so we used like the unbiased variance estimator. That's what we used in here. Yeah, it's a good point. But like in terms of the understanding, the thing we were really trying to get at is this quantity here. Yeah. Okay, good question. Any other questions? Okay, so last thing, let's say that we're not interested in mu anymore. We actually want to estimate the variance in this random variable. So we want to estimate V. So we learned, highlight it, estimate V. Okay, so we learned in unit one particular way of doing this, and it was the sample variance. So in this case, you have just an average of these squared values. And when we did the average, we're taking just 1 over n, this thing you would probably think of to do first. So that's great. So, we have this estimate now of V. Is it going to be perfect? No, definitely not perfect. Next question, is it at least unbiased? Is it at least on average correct? Unfortunately, it is not. So when you look at the average value of SZZ, it's a little bit less than the true V. As it's what we call asymptotically unbiased, and that as n goes to infinity, it eventually catches up and is true. But for any finite number n, it's going to be a little bit less. So this is a biased estimator. And sometimes you think, I don't like that. I don't like the fact that my variance estimate is always a little bit less than the true variance. So to get around this, there's a very simple fix. You just change this n to an n minus 1. Essentially, you're multiplying this by n over n minus 1. Like I'm multiplying this n over n minus 1. And when I do that, I'm canceling out this factor. And now you're going to get an unbiased estimate. So this is the second way. When you multiply this by n over n minus 1, you get this guy. And this is the one that we said is the unbiased estimate of the variance, this choice. And we're going to call it xi, ZZ. Okay, so now you might feel better about xi because you know that although it's never perfect for any given realization of this, on average, they are correct. So that's the difference between the biased and unbiased versions of the sample variance estimator that we've seen a couple times. Okay, questions on that? Okay, you probably have seen this in other courses. The very last thing I want to say is that, so which one is better? Is this one better because it's unbiased? So it turns out it depends what you mean by better. So if what you care about is mean squared error, you can do an analysis of the original one, mean square error of SCZ. So you're looking at the expected value of the square difference between this and the truth. And you can do an analysis of this one, and you get these two expressions. And it turns out, it's maybe not obvious, but you can also show that this one is strictly less than this. Okay, so what that means is that the original sample estimator here is, we're almost done. Okay, all right. Thank you. So, so basically, from the mean square error perspective, this first one is better. Okay, so even though it's biased, it's better from a mean square error perspective. Another way to think of that is it has a higher variance. In the bias variance decomposition, its bias is lower, but its variance is higher, and eventually this guy wins. Okay, so so with that, we're done. Sorry for going over time, and I'll see you guys on Wednesday.